Today, let's look at the 32-bit ARM architecture. So today we're going to look at the ARM architecture from an overview perspective, then the actual ARM register set, and then we'll look at the current program status register. So to start off with, the ARM architectures define a family of RISC processors, or reduced instruction set processors, that are suitable for use in a variety of applications. ARM processors are very popular these days, as we'll see. So processors based on ARM are used in designs requiring a combination of high performance, low power, and small physical size. So for example, the Garmin watch that I use to track my fitness levels in my running. So many applications of the ARM architectures are what we call system-on-chip designs, or SoC designs. And they combine a processor with specialized hardware depending on, the size of the device, what the size requirements are, etc. So for example, another example would be cellular communications in smartphones. Now, ARM processors serve as embedded processors also in safety critical systems, such as anti-lock brakes as an example. Also in smartwatches, smartphones, which I'm sure most if not all of you have, tablets, and other similar style devices. Now, as of 2021, how popular is the ARM architecture? 180 billion ARM processors, as an estimate as of 2021, have been manufactured. Now, ARM processors are what we call true RISC systems, so reduced instruction set systems. And they use general purpose registers. And they use the single cycle execution for most instructions. So a separate variable length instruction set named T32, formerly called Thumb, is available for applications where memory is at a premium. So if we have very small devices with very small space, then we can run what's called T32. Now the T32 instruction set uses a mixture of 16 and 32-bit instructions. So the advantage, of course, of that is if we want to run instructions that are very small in size, that take up very little space, we can run them as 16-bit instructions, right? So that there's an advantage to that. So current ARM processors support both ARM and the T32 instruction sets, and they can be switched on the fly. So this is a big advantage of the ARM architecture. Most apps, though, prefer the T32 mode because code density is improved. So in other words, the code that we write to run on those devices is better at fitting into smaller spaces, which a lot of these devices have the requirements for. So if you can think of this watch as an example, very small device, not a lot of memory space compared to a laptop as an example. So the more code we can fit onto that smaller space, the more functionality, of course, that particular application on that particular device can have. So ARM is what we call a load and store architecture, so requiring data to be loaded from memory to a register before any processing can take place. So once that information is there, then it can execute super fast, right? So this permits several sequential operations then to be performed at high speed on an operand. So once it has been loaded into one of the many processor registers, then bang, 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 we can go through those instructions very fast because they're all small and concise. So the ARM architecture supports a couple of different data types. So first off, a byte, right? We all know what a byte is by now, 8 bits. Also a half word, which is 16 bits. So this is important, right, for the T32 functionality, right, where we're executing instructions that are 16 bits in length. And then also 32 bits, which is referred to as a word. And then lastly, a double word, which is 64-bit. So if we're not so concerned about space, we can do 64-bit data types as a double word. ARM also supports 8 distinct execution privilege levels, so listed here. So user, supervisor, fast interrupt, IRQ, your typical IRQ, monitor, abort, undefined, and system. So for the purpose of operating systems and user applications, the most important two privileges then would be, of course, user and supervisor, or SVC. The two interrupt request modes, FIQ here, fast interrupt request, and the IRQ, the interrupt request here, are used by device drivers for processing interrupts. So most operating systems running on ARM, including Windows and Linux, if we have Windows or Linux running on an ARM system, the kernel runs in ARM SVC mode. So the kernel, right, the core, runs in SVC mode, which is equivalent to ring 0 if we're talking about an x86, x64 architecture. And then the user mode here, USR, is equivalent to running on ring 3, right, on the x86 and x64 processors, if we're comparing kind of how each of these functions in kind of the same way. Now, ARM has evolved over the years to the current variant, as of 2021, of course, is the ARM v8A. And it supports 32-bit and 64-bit operating systems and applications. And virtually all high-end smartphones and portable devices produced since 2016 are designed around this ARM architecture. So it's very, very popular and in very high use. So it's worth having an understanding of how the ARM architecture all works. So the register set in user mode, it has 16 general purpose 32-bit registers. So similar to what we saw with the x64, right? Remember the x64 had 16 registers. But in this case, they're general registers, so R0 to R15. And the first 13 are truly what we would call general purpose. The 14th register, R13, because of course we're starting from 0, is the stack pointer. So it points to where we are on the stack. And R14 is the link register, which holds the return address while in a called function. So we have to go somewhere to execute a function call. Then we have somewhere to come back to, of course, with the link register. And then R15, the final register, is our program counter. Okay, so those are the registers that have a little bit more specialization. The other are just general purpose. The current program status register, or the CPSR, contains all the status and mode control bits. So basically what mode we're in, and then also our flags. So similar to the flags registers in the x86 and 64 architecture, we'll take a look at a table here in one sec, actually right now. Here's our CPSR functions. So looking at first the mode, right, or M, you can see that we have 3 bits assigned to that. So the current execution privilege level. So again, the two most common, user mode and supervisor mode. So this is the equivalent user mode of ring 3 in the x86, x64 architecture. And then this is kernel mode, or mode 0, or ring 0. Also, we have thumb, right? So T32, if it's active, we can, for example, run 16-bit code that optimizes space better. And again, that's desirable on devices that are compact and have minimal memory. Endianness, whether it be little or big endian. So most code uses little endian mode, just so we know where to start within a register. Cumulative saturation flag, if an overflow or saturation has occurred, and then we get into our flags. So our overflow flag, our carry flag, our 0 flag, and our negative flag, all of these flags, depending on what our current status is. Okay, so that's our current program status register, or CPSR. And that's all I wanted to talk about in this session. We'll continue on this session in the next video. So we looked at the 32-bit ARM architecture. We looked at the 32-bit ARM register set. And we looked at the current program status register, which gives us different statuses depending on, for example, what mode we're in, whether we're in user mode or supervisor mode, and whether we're setting a carry flag, a negative flag, a 0 flag, etc. Okay, so that's all I wanted to talk about in this session, and we'll continue our discussion of the ARM architecture in the next session.